Hi, I'm Alistair, and on this channel I describe how to create playful electronic projects. Now, there's lots of existing tutorials out there that show you how to use specific electronic components, how to make an LED blink, or how to make a motor spin, or how to read a button input. And many of these are great resources. They'll comprehensively explain how to use a single component in isolation. And obviously that seems logical if you want to learn only the relevant details of that particular device. But it means that they often don't describe some of the issues you might need to consider when implementing several of these components together as part of a wider, slightly more complicated system. Most useful electronic circuits don't only have a single component acting in isolation. They'll have many different modules. There might be LEDs, displays, motor drivers, sensors, and they might be connected using different sorts of interfaces like SPI, I2C, UART, and they might be operating at different voltages or sending and receiving data at different speeds. And the code required to control this different hardware becomes more complex too. How do you set the position of two servos independently while also updating an LCD display and listening for button input, for example? Now, one thing I've generally tried to do on this channel is to make tutorials that demonstrate complete projects. So I've often described specific examples of these sorts of issues, such as conflicts between two components, as they relate to a particular project. But I've never really described in general terms the considerations for building slightly more complex electronic systems. And when I looked around to research this video, it seems that not that many other people have done either. There's either beginner level stuff or there's forums for professional electronic engineers, and there's not that much in between. So I wanted to share with you some what I would call general intermediate level knowledge relevant to real world Arduino or ESP project design when you want to do something a little bit more complicated than just blinking an LED. Some of the problems you might encounter and how to get around them, share some tips and tricks and things I wish I had known when I was first doing this. So rather than just saying copy and paste this code or wire it like this, I'm going to try to explain what's happening, but it's not going to all be theoretical. I'm going to give you some practical examples of how to use this knowledge using examples from various escape room props I've built over the years. And so in this first video, I want to start off by talking about GPIO inputs and outputs. So every microprocessor has GPIOs, general purpose inputs and outputs, and those are exposed on these pins around the edge of the board. And that's the way that the processor interacts with the outside world. So you can set them as output to write data to other devices, or you can set them as an input to read incoming data. And that data is encoded based on the voltage at the GPIO pin. Now, most GPIO pins are digital, so they can have one of two discrete values. They're either high or low. And that definition of high and low relates to the voltage at the pin relative to a somewhat arbitrary 0 point, which we call ground. Now, ground is also one of the pins that's exposed around the edges of the board. Sometimes you might have several ground pins, which are provided for convenience. They're all connected together, so they're all interchangeable. And whenever you want to connect an external device to a GPIO pin, you generally also want to connect the ground pins from the device to the processor to create what's called a shared ground. So they've all got this common point of reference. It's like calibrating them to the same 0 point, which means that they can then agree on whether the signal at the GPIO pin is high or low compared to that ground. Now, a low signal generally means that there's no potential difference between the voltage of the pin and ground. The voltage is 0. But what constitutes a high voltage differs between devices. And that's what we call the logic level of a device. So Older boards, such as the Arduino Uno, Nano or Mega, are 5-volt logic level devices. So a high signal on the GPIO pin of this device corresponds to 5 volts above ground. Newer devices, such as an ESP8266 or ESP32, operate at 3.3 volt logic level. So that means that a high signal for them is only 3.3 volts above ground. Now there's actually a bit of tolerance in those measures. On an Arduino Uno, any voltage above 3 volts will be treated as high, while any value less than about 1.5 volts will be treated as low. But when we talk about the logic level, we're referring to the top end, the ideal value that would define a high voltage at that pin. Now, one of the first digital inputs you might try to read on a GPIO pin is a button. And one thing that sometimes gets people confused is that in our heads it feels natural to think that when a button is pressed, that correlates with something being on, so you tend to think that that would make a connection to a high signal to be read at a GPIO pin. Then when the button is released, it breaks that connection, turning it off, and we associate off with a low signal instead. But that's not the case. Suppose you were to wire your button to a GPIO pin like this. Now, when you press it down, it makes a connection, a circuit through to 5 volts, which sure enough would read as high. But when the button is released, the GPIO input pin is not connected to anything. Now that doesn't make it low. Instead, it's what's called a floating input. It's just going to pick up background electromagnetic noise and may randomly flick between a low or high value. So we need to give it a default state when the button's not pressed, and that's where pull-up or pull-down resistors come into place. So in this circuit, we could add a pull-down resistor here. When the button is not pressed, this gives the GPIO pin a path through to ground. So it's going to read low. We're pulling the signal down to a low value, and the resistor has the effect of limiting the current. Now when the button is pressed, we create an alternative path in the circuit that goes to 5 volts instead, which is a high signal. Now the crucial thing is that because there's not a resistor in that path, the current chooses the path of least resistance. It goes this way instead, so it overrides the default pull-down resistor. Now, by convention, a more common way of reading switches is using a pull-up resistor instead. This is almost exactly the same logic, but applied in reverse. So when the switch is not pressed, we have a circuit that goes up to a high signal, 5 volts, through a resistor. And when the switch is pressed, it pulls the pin down to a low signal by connecting directly to ground instead. And this is how you'll find almost all switch type inputs like buttons wired up. Although it might seem counterintuitive at first to have the default state as high, that's actually preferable. It's more resistant to noise, and it means you can use open collector devices. These are devices that don't ever drive a signal high. All they do is pull it down from its default state to ground. And that's how the I2C interface works, for example. And most microprocessors, including all Arduino and ESP boards, have built-in pull-up resistors on their GPIO pins already. And you can enable these in code, which means you don't have to have this external resistor in your circuit at all. You can wire any button input directly between a GPIO pin and ground, like this. Now, setting a GPIO pin as an output is how you get your microprocessor to control other devices. If you then write a high signal to the pin, it gives it a positive voltage, and that's going to cause current to flow through any connected wire through to ground. And that brings us onto the question of voltage and current that will flow through that connected device. So, just as microprocessors have different logic levels, so too do the other devices that you might connect to their GPIO pins. LCD displays, programmable LED strips like NeoPixels, and most motor driver circuits operate at 5 volts. whereas GPS modules, OLED displays, SD card readers normally operate at 3.3 volts. So that gives us 4 possible scenarios. You might be controlling a 5 volt device from a 5 volt logic level controller. And this is easy. You can then wire the device directly to the appropriate GPIO pins. Or you might be controlling a 3.3 volt device from a 3.3 volt logic level controller. And that too is very easy. You can wire them directly. But what about if you wanted to control a 5 volt logic device, but you were using a controller that only operated at 3.3 volts? Well, that might be okay. It depends on the device. As I mentioned earlier, there is some tolerance in what is acceptable as a high signal. A 5 volt device doesn't need to see exactly 5 volts to interpret that as high. Many will still interpret 3.3 volts as high, in which case you might still be able to connect them directly. When the processor here sets a high signal, it only gets as far as 3.3, but so long as that is within the tolerance of the sensor, that's still high. But that's going to be on the limit of many devices. So if you get strange behavior, you may have to consider using a logic level converter to step up the signal instead. And what about if you wanted to control a 3.3 volt logic device, but from a controller that outputs 5 volt at the GPIO pins? Well, this is the worst possible combination. Some 3.3 volt devices are described as what's called 5 volt tolerant, which means that even though they operate at 3.3 volts, they will still accept a 5 volt signal, in which case you could directly connect them. But if they're not tolerant, that could very easily damage the board. Now you might be able to step down that 5 volt voltage to 3.3 volts using a resistor divider circuit, and you'll have seen me use them in many previous projects, such as when I connect a DF player to an Arduino. But again, you might prefer to use a dedicated logic level converter. Now the problem here is that in every case when you convert a signal, there's the potential to introduce noise or to affect the signal quality in some way, to slow it down. And so even though logic level converters can potentially correct the problem of having the incorrect voltage, they may actually introduce other errors as well. There's lots of different sorts of logic level converters, so it's very important to select one that's appropriate for the application you're trying to use it for. Now let's talk about current. So when we think about voltage, you might think about batteries which are used to power a device. So if you've got a 5 volt device like an Arduino, you might think, great, I can power any 5 volt device by just connecting it to a GPIO pin, writing a high signal to that pin, and then letting current flow through it. However, it's important to notice that we describe these as 5 volt logic level devices. The GPIO pins are not actually designed to provide power to any significant load like a motor. Instead, they're used for transmitting logic signals, highs and lows, that tell the motor to turn. They don't actually provide the power necessarily for it to do so. Now, a GPIO pin can typically only source about 20 milliamps of current. A motor might draw 1 amp, which is 50 times that amount. So to provide that kind of current, you need to use a transistor. Now, a transistor is like a gate. A relatively small current from a GPIO pin opens or closes the gate, and that allows a much larger current direct from a power supply to flow to the motor or whatever other load it is you're trying to control. Now, there are specific driver chips for things like LEDs and stepper motors, and there's also general purpose transistor arrays. You'll see a lot of projects use chips like UDN2981 or ULN2803, which allow you to switch 8 channels of high current from 8 GPIO pins. But remember, generally speaking, you don't want to directly source power for anything from a GPIO pin beyond maybe a simple LED. You just use that for transmitting data at a logical high or low value. Now, some GPIO pins allow you to output an analog signal, i.e. a range of values, not just high or low. And you might think they do that by setting a different analog voltage at the pin, but they rarely actually do that. Instead, what they do normally is something called pulse width modulation, or PWM. Now, PWM works by rapidly switching the digital output of a GPIO pin between high and low. And the frequency at which it changes between those values can be adjusted, but it's generally several thousand times a second, so it's very fast. And by varying the proportion of time spent in the high state compared to the time spent in the low state, which is something called the duty cycle, that adjusts the average voltage at that GPIO pin over a period of time. So suppose you have a 5-volt output device like this, but then you apply PWM with a 75% duty cycle. So that means it spends 75% of its time in the high state and 25% in the low state. So that's going to give you an average voltage of 75% of 5 volts, which is 3.75 volts. And by adjusting the PWM duty cycle to range between 0 and 100%, that's how you could dim an LED light, for example. Now, PWM control generally requires the use of a particular timer hardware on the processor, so not every GPIO pin supports it. On an Arduino Uno, you can tell which pins they are because they're the pins with these little squiggles on them. So they're pins 3, 6, 5, 9, 10 and 11. So there's 6 pins on Arduino Uno. On an ESP82, I believe any GPIO pin can be used to support PWM output. Now, some GPIO pins also allow you to read an analog input. So value from a light or a temperature sensor, or inputs from a potentiometer or an analog joystick. And this is done with a part of the chip called an ADC, or an analog to digital converter. Now, on an Arduino, the pins that can be connected to the ADC are those labelled with an A. So an Arduino Uno has 6 analog inputs, A0 to A5. The ESP32 has 15 pins that can read an analog input, whereas the ESP8266 only has 1. Now, the ADC reads the voltage at the specified GPIO pin and converts it to a number. But the resolution of that number varies. An Arduino has a 10-bit ADC, so it can represent the voltage at one of the analog pins with a value between 0 and 1023. An ESP32 has a 12-bit ADC, so it maps the voltage to a value between 0 and 4095. It's got a higher detail of resolution. And then you can use that digital value in your code however you want. Okay, so GPIO pins are essential to making your microprocessor being able to interact with things. Every time you want to connect a sensor or trigger an output, you're going to need at least one available pin. But there's only a limited number of GPIO pins available, and different microprocessor boards have different numbers of them. So an Arduino Uno has 20 GPIO pins, of which 6 can read analog inputs and 6 can generate analog outputs. A Nano is the same, other than the fact it actually has 2 more analog input pins that can be directed to the onboard ADC. An ESP8266, like this D1 Mini, has 17 GPIO pins, but you can actually only use 11 of them because 6 of them are already connected to the flash memory chip. And it's only got a single pin that's capable of reading an analog input. You can get ESP32 boards with different numbers of GPIO pins available. 30, 36 and 38 pin variants are common. But beware, even though some boards sound like they've got more GPIO pins, they too are actually already being used by some of the hardware on the board to connect to the onboard flash chip. So it's actually pretty useless to have them exposed on the side of the board. So what happens when you run out of GPIO pins on one of these devices? Well, years ago, the advice might have been to upgrade to a different board, such as an Arduino Mega, which is much more capable, has more available GPIO pins, but it's actually pretty old hardware now. And there's a much better alternative than having to change your entire underlying board. And that alternative is one of these, which is a GPIO expander. Now, before getting into the detail of how these work, I did promise that this video was going to have some practical examples, not just theory. So let me give you some scenarios where you might run out of GPIO pins. And the first is if you are using an LCD display like this one. Most LCD displays have a Hitachi HD44780 chip on the back. And when you use it in its default mode, it uses 11 pins on the base here. There are 3 control lines and 8 data lines. Those 8 data lines correspond to 8 bits that are either high or low, and that allows you to load an entire byte of data representing a character all in one go. It also has a 4-bit parallel mode instead, which means you only need 4 data lines and you load the byte value in 2 batches of 4 bits, but that still requires 7 pins on the bottom. Now this is a matrix keypad. Now this is an input that requires lots of pins because these are arranged in a matrix where you need 1 GPIO pin for each column and 1 for each row, and then you scan across them. And you'll find plenty of examples that will demonstrate how to wire these 2 components up to an Arduino individually. But you won't find very many that tell you how to do them both at the same time, because as soon as you do that, you begin to run out of GPIO pins. However, introduce your 3rd component here, that is your GPIO port expander, and you are able to connect both an input and an output, and in fact many more inputs and outputs, using only 2 GPIO pins. So let me show you it in action. Here I've got an Arduino Nano which I've inserted onto a screw shield. This just makes it easier to connect components to any of its GPIO pins through these little screw terminals at the edges. And I've already wired a connector to 4 of those pins, which is using the 2 pins A4 and A5 together with ground and 5 volts. Now, the choice of these particular pins is important. Just as I described that there are only some pins capable of analog input and some capable of analog output, there are also some GPIO pins with other special features. And these 2 GPIO pins are the ones that are used by the Arduino's I2C interface. A4 is the data line and A5 is the clock line. Now, I'm not going to go into too much detail about I2C here, that will be the subject of another video, but the thing to know is that I2C is a bus interface. So rather than use a GPIO pin to send or receive high or low signals to a single device, it can send and receive data to many devices, all connected to the same shared clock and data pins. Every device on the bus has a unique address, and the Arduino is able to route data to a particular device by including that address as part of the data packet it sends. Now here I've got a PCF8574 port expander. That's the chip in the middle, and it's been mounted onto a breakout board. Now this is an I2C device, so it communicates with the Arduino using these 2 lines. Now it's got some jumpers on the board here which let you assign an I2C address to the chip, and then at the top of the board it's got these 8 pins which correspond to the 8 additional GPIO ports that this chip provides. So when I plug it in like this, the Arduino can send a message to the PCF8574 over the I2 interface here, and it can tell it to write a high or a low value to these pins. Or it can ask the chip whether the voltage at these pins is high or low. So they act pretty much the same way as if we were to do a digital write or a digital read to one of the GPIO pins on the board itself. We've connected the ground line together, which gives it that common low reference, and because we're using an Arduino Nano, we've connected the VCC to 5 volts. So that defines the voltage that the chip here uses to set a high signal on any of these pins. If we were using a 3.3 volt logic device, we could have supplied 3.3 volts on this line instead, and then high would only have been 3.3 volts. Neat, huh? But it's about to get even cooler, because at the end of the board here, you'll see that there are 4 more pins. And these are the same data and clock, VCC and ground lines as at the other end of the board. They literally just pass straight across the board and out the other side. And because I said I2C was a bus interface, that means we can plug more and more I2C devices onto the same bus without using any more GPIO pins or making any differences to the Arduino at all. All we have to do is make sure that each one of these devices has a different I2C address, which we do by moving the position of these jumpers. Now, there are 3 jumpers and each one can be in one of 2 positions, so that's 8 different addresses. So you can have 8 of these modules chained together on the same bus. Each one gives us 8 more GPIO pins for a total of 64 GPIO pins, which are accessible from the Arduino. You can actually also get a variation of this chip called the PCF8574A, and that has a different range of 8 I2C addresses. So you can also have 8 of those for a total of 128 GPIO pins. So we've got all these available GPIO pins. Let's do something useful with them. And the first component I wanted to plug in was my 4x4 matrix keypad here. So I've connected a ribbon cable to the bottom. I've got 4 column pins and 4 row pins. And I'm just going to wire that up to the 8 ports of my first PCF expander. There we go, that's a bit clumsy, but we got it there. Now, the next device I wanted to connect was an LCD display. And in fact, using these port expanders to reduce the number of pins required by an LCD is such a common way of using them, they actually made a module particularly designed for that purpose. And here's one, it's called an LCD backpack. So functionally, this board here is exactly the same as the first module I showed you. It's still got the same PCF8574 port expander chip. It's got the ability to select from one of 3 addresses. The only difference is that it's been laid out slightly differently. So instead of having just 4 general purpose pins across the top, it's had the outputs from the port expander mapped into a row of 15 pins here that line up with the 15 pin interface that you get at the bottom of an LCD display. So there's 3 control lines, there are 4 lines used for the parallel interface in 4-bit mode, and then the final channel from the port expander is used to control the backlight instead. And then it simply slots on from the back of the LCD there and gets soldered through the front of the pins. So I've already attached one of these onto the back of this LCD display, and I can simply chain that onto the output of my first. So now I've got 2 PCF8574 chips daisy chained together on the same bus, and I've got 2 different devices using them. I've got my keypad wired to 8 of the ports here. I've got my LCD display wired to 8 of the ports on the back of that one. Now I'm just going to turn my Arduino on. If I just so here we go. Hopefully you can read the LCD display there. So I've got that displaying hello world. That's obviously working as an output. And now if I press some of the digits on my keypad, so do 1, 2, 9, A, D, you can see I'm registering the keypad input as well. So that's really it for the wiring. Now, because these aren't actual GPIO pins directly on the Arduino board, you don't quite control them in the same way as you would do with a built-in GPIO pin. You have to adjust your code slightly. So let me show you the code that I'm running for this example. And here it is. Now, to use any I2C device with an Arduino, you need to include the wire library, which I've done at the top. This is built into the Arduino IDE, so you don't need to download anything special to access it. You just need to incorporate it in your code with an include command. Now, to use the LCD display, I've also included another library, which you can download from here. And this library has got two parts to it. This one here controls the drawing functions for the LCD, so to print characters, to move the cursor to different lines, etc. But it also has this extension library, which includes the I2C interface to those functions. So combined, they provide a wrapper that's going to let me control the LCD display. For the keypad, however, the input, I've not included any other library at all. I'm going to write my own functions directly against the wire library, just to demonstrate how you could do that. So I go into the constants, and the most important constants I'm defining here are the I2C address of the two devices which are attached to my bus. So I've got hex addresses of 0x20 and 0x27, and that corresponds to the position that I set those jumpers in on the two boards. For the keypad, I'm also defining an array of characters that correspond to each of the 16 keys on the front. That's just so I can print them out on the display. And also I'm going to define the number of rows and columns. You can get keypads that are 4x3 or 1x4, but this is a 4x4 display here. In the global section, I'm going to create an LCD object that is based on that HD44780 library. I'm not going to create anything for the keypad at all because I don't have a library object to create, but I am just going to keep track of what the last input I read from the keypad was. That will let me know whether a new key has been pressed this frame or not. Then I go on to the setup function. And this is the bit which I want to focus on here, because this is how we actually initialize communication with an I2C device like the port expander. So first of all, you call the wire begin function. That initializes the I2C interface. And then we actually start a transmission to a particular device on the bus. And as I mentioned, the way you do that is by specifying the address of the device that you're trying to communicate with. This was the single byte value we defined at the top. So we're going to talk to the keypad to start with. And having decided what device we are trying to communicate with, we then send it a value, and it's going to be a single byte value. So I've expressed it in binary format here. So these zeros and ones here are individual bits which are going to be combined together into an 8-bit single byte value that we're going to write over the I2C bus, over that SDA line that we connected to this device here. And what this is going to do is this is going to set the input modes of the 8 ports on the PCF8574 chip. So unlike the pin mode function that you'd normally call in Arduino, that you specify a particular GPIO pin and say whether it's high or low, when you're communicating with a port expander like this, you set the high or low values, or the input or output values, sorry, of all 8 ports simultaneously in a single byte that you send. Now, to read the keypad, what we want to do is we want to set the columns as inputs, and we're going to set the rows as outputs. So to do that, an input corresponds to a 0 value, an output is a 1, so we're going to send 4 zeros, then 4 ones. And then to actually send that byte of data, we call the end transmission function. And that is the basic structure of how you communicate over an I2C interface. You begin a transmission with a named device, you write a byte of data to that device, and then you call the end transmission function, just kind of close the packet off. Now for the LCD, because we're using that library, which I mentioned at the top, kind of wraps around these functions, you can simply call the functions provided by the library. So here we've got a begin method that starts with 16 columns and 2 rows of display. It sets a backlight value, it prints a message to the screen. But inside the library, all of these functions here are being translated to commands that look like this. It just adds an abstraction layer because this is generally a little bit prettier and a little bit easier to understand what's going on. But if you wanted to, you could hard code all of these values yourself using these raw commands. Okay, so I wanted to sort of show you both approaches of doing it here. And then in the loop function, what do we do here? Well, we're going to call a method called getKeypad to work out which key is being pressed, if a key is being pressed, and if the key is different to the last input we pressed, because I don't want you to just hold down a keypad key and get repeated inputs. So I'm going to make sure it's different from the last input. Then we'll print it on the LCD. I also send it to the serial monitor, and then we update the value. So all of the logic is really being done in this function here, and that's the last function in the code. So what do we do here? Well, here we're going to call another method, which is called the wire request from method. So this, whereas we were beginning a transmission before to initiate data transfer to the device, here we are requesting data from a device. And again, we say the address of the I2 interface that we want to request data from, so of the I2 device. We're going to request 1 byte of data from the keypad, and we're going to read that byte that is received into a value called keypad state. And then what we're going to do here is just look at the value that that contains. Now initially we set it to be, if you recall, 4 zeros and 4 ones. That was the initial high-low value of those pins. If the value we've received back from reading that byte of data is different to that, then it means that a connection must have been made between some of these columns and rows in the matrix. In other words, at least one key is being pressed down. So then what we need to do is we work out which key it is. And we do that by looping over the columns and rows in turn. So we now need to change the state of the keypad, so we'll send a new byte of data to it, and what we're going to do is we're going to loop over the columns here up to the total number of columns that are on the keypad, and we're going to shift the value 1 to the left, essentially by the column we're on at the moment plus the number of keys there are in each row. Now this is a little bit tricky to explain what's going on here, but essentially what we're doing is we are trying to work out the intersection between a given row and a given column. We know that there are num key rows in each column, and we're looping over the number of columns, so each time we go through this loop we want to add on that number to the column number we're on at the moment, then we shift 1 left that many, and this is going to give us the position through this 8-bit value here that corresponds to one of the columns. And we'll read that value back. Again, this is another byte of data. We're always working at the byte level, generally speaking, when you're dealing with I2C interfaces backwards and forwards. That's why it's very convenient to have 8 ports in a given expander, because you can communicate with all 8 ports in a single byte. So we'll read what the row state is, and now what we need to do is we loop over all the rows in that column we've retrieved, and we need to work out if any of these was the one that had changed from the initial key state value. So again, we shift left through over all the bits, and if we find the one that has differed, then what we do is we look up the label from the key labels array. So that was the array I defined at the top here, that just gives a single character which is written on the front of each key. So this is the 0th index, the 1st, 2nd, 3rd, 4th, 5th, 6th. You know, the eighth element in this array is not necessarily the number 8, because you could have all sorts of things written on this keypad. So we actually look it up by its position, its column and row position, and then we return that response. And once we've done all that, what we then have to do is just reset the inputs and outputs of the port back to their default state again, so we're ready to read the next keypad input. So this is obviously a little bit more complicated if you're not familiar with working with bits of data and bytes of data. So for that reason, that's why you might find it more convenient to look for a library that basically just encapsulates all that functionality in something a little bit easier to use. But I just wanted to demonstrate that you don't have to do that at all. It's not actually that bad. You can write your own functions directly against the wire library and just rewrite all your code instead of using pin modes and digital writes as you would do normally. So port expanders like these PCF8574 chips are great. You can buy them in convenient ready-made boards that slot onto the back of an LCD display, or with just a generic row of pin headers so you can connect them to any input or output you want. You can daisy chain up to 8 of them together to get literally hundreds of GPIO inputs and outputs. And they can operate at 3.3 volt or 5 volt logic, which means that you can use them with pretty much any controller so long as it has an I2C interface. And then they only use up 2 pins to do so. Now, they don't quite have the same capabilities as built-in GPIO pins though. For one thing, they are digital only, so you can't read an analog input on these pins, and you normally can't write a PWM analog output either. And they also don't have built-in pull-up resistors. So you can set them to the equivalent of the input or output pin mode from an Arduino, but you can't set them to the equivalent of input pull-up. You'd have to explicitly add external pull-up or pull-down resistors into your circuit, as I showed you earlier. Also, they're not quite as fast as built-in GPIO pins because there's that extra layer of abstraction from the microcontroller. The I2 interface that they use carries the signal from the processor to the chip, typically at a clock speed of 400 kilohertz. So that is still way fast enough to deal with anything involving human input, like a button or a switch, but it might be a factor to consider if you're dealing with sending data between very fast devices. Now, there are some alternative port expanders I should mention as well, and the most useful one of those is one of these. This is an MCP23017. Now, this chip does have built-in pull-up resistors on each of its channels, and it's also got 16 channels rather than the 8 of the PCF8574. And each of those channels also has individual interrupts. So it's much closer to having feature parity with the inbuilt GPIO pins than the PCF chip does. It too comes with an I2C interface, but it also has a variant that uses an SPI interface from the controller to the chip instead of I2C. Now this uses up one more pin of the Arduino or the controller, but in return it is significantly faster. It's a 1.7 megahertz connection from the processor to the chip rather than the 400 kilohertz of the PCF8574 I2C interface. But it is also significantly more expensive, whereas these really are very cheap and easy to obtain. Now, I'll talk more about some of these interfaces I've mentioned, SPI, I2C and others in another video. But I hope that in this video I've explained some useful details about working with GPIO pins in general, some of the details about them and how you can get more of them for your projects. If you have any questions about anything I've said, please do write them in the comments below and I'll do my best to answer them. You can follow this channel for further videos in this series or check my Patreon page for further details of my escape room projects, which show you some of the practical tutorials where you might apply this kind of knowledge. And other than that, I just want to say thank you all very much for watching and I look forward to seeing you again next time. Okay, cheers, bye.